Okay. All right. Okay. In theory, we're live. As always, we require some external person to collapse the wave function and let us know that we exist. The moon looks nice today, Jack. Looks like a good day on the moon for you.
It is a good day on the moon, but for me, every day is a good day on the moon if we can actually get there and start building our telescopes.
Yeah. All right. So I guess let's get started and just let people know who you are and what you do.
Yeah. Well, I'm Jack Burns, and I'm a professor of physics and also a professor of astrophysics at the University of Colorado in Boulder. And I run a NASA-funded center called the Network for Exploration and Space Science, funded by the NASA Survey Institute, which is Solar System Virtual Exploration Research Institute. It's a mouthful for an acronym, but and what we're doing is principally investigating, as I've been doing now for over 35 years, putting radio telescopes onto the moon, particularly on the far side.
All right. Now I did a video about your project probably about 2 years ago. I don't know if you ever saw it, but let's sort of talk about why the moon is the perfect place for a radio telescope.
Yeah, it's a great question. The moon, rather than the Earth, is perfect for low radio frequency astronomy, and I emphasize the low radio frequencies. So these are below the FM band, so below 100 megahertz down to a few megahertz. That you've got several problems on the Earth. First of all, the Earth is swamped with radio frequency interference from military and commercial transmitters, from satellites. So that's problem number one. Problem number two is the ionosphere. That layer, that ionized layer of the atmosphere, radio signals that come into the ionosphere, they get distorted, much like optical light gets distorted by the turbulence in the troposphere. But in this case, it bounces off of the ionospheric layer, and it distorts the signal, so we don't get clean looks at the universe. In fact, at frequencies below 10 megahertz, the ionosphere is even opaque, so it bounces signals back into space. And then a final reason that the moon is nice is because it's very stable and it's uniform. And so that's a problem on the Earth. When you set up radio telescopes on the Earth, you've got changes in moisture, changes in the subsurface conditions due to moisture, vegetation on the Earth. All of that distorts our radio beams in ways that make it very difficult to see these weak cosmological signals that we're looking for from the early universe.
So I know that there's certain wavelengths that work fine on, I guess, all wavelengths except for maybe like long radio waves are hampered by the Earth's atmosphere. Like infrared isn't great. Even visible light, the atmosphere is this awful soup. Blocked entirely, X-rays, certain forms of infrared, gamma radiation, that kind of thing.
Right.
And so you're sort of in that same realm that it's not blocked, but it could be better if it wasn't in
We
Earth's
are.
atmosphere.
Yeah. I mean, it's blocked. It's distorted. It's kind of like also in millimeter wavelengths, which is the far infrared. Some of that penetrates to the atmosphere, but a lot of it's blocked and distorted. And in the case of the low radio frequencies, this is really the last unopened window to the electromagnetic spectrum. We've been doing radio astronomy from the ground since the 1930s, really, and particularly the 1950s, but not at these low radio frequencies, and especially not to look for such weak signals as coming from the early universe.
So then let's talk about what the value is of seeing this wavelength specifically.
Yeah. Well, one of the things that it not only do we open up that window, the electromagnetic spectrum window, but we also open up a window to a part of the universe we've never been able to explore before. And that's called the Dark Ages and the Cosmic Dawn. This is a time period, the Dark Age, called the Dark Age because this is before the first stars and galaxies form. And it's right after that time period where we see the cosmic microwave background. So first light in the universe, as some people talk about it. The universe at that point, having no point sources of light, is dark. But there's a lot going on. That what will become stars are collapsing, and the universe is filled with neutral hydrogen, which is very important on how we can be able to probe it. And then a little bit later, then those collapsing cores form the first generation of stars, and they turn on and they emit ultraviolet light, which then begins to ionize the intergalactic medium. So that, we think, roughly is how those first stars are born. But the problem is we have no actual data.
Right.
Hubble Space Telescope and even the upcoming James Webb Space Telescope, the individual objects are way, way, way too weak to be able to see, even by those powerful telescopes. But as I mentioned before, the universe at this time is filled with neutral hydrogen. So even a modest-sized radio telescope on the moon in the right location can at least begin looking at the global or all sky signal coming from the time period of the Dark Ages and the Cosmic Dawn. You just need to go to the right place in order to be able to see it.
Right. Okay. So I just want to sort of cover this timeline of the universe, right? So we've got the Big Bang. We've got the entire universe was essentially like some form of star for the first 370,000 years until it could finally cool off to the point that light could escape. And right. That light that we see, that's the cosmic microwave background everywhere. And then the universe was essentially hydrogen and helium left over from the Big Bang that was no longer kind of glowing red hot and no longer opaque to light. But it hadn't formed those first stars, and then those stars hadn't gone into galaxies, and we see the structures that we see today. So if you could travel back in time and just sort of look around with your eyeballs, what would you see at that time?
Yeah, well, before the when you're in the Dark Ages, you wouldn't see anything. It's dark.
Yeah.
I mean, with your eyes. But if you had a radio telescope, the universe would be filled with radio emission coming from the hydrogen, because it turns out the ground state of neutral hydrogen has this very interesting property of what's called a spin flip transition. So you get the electron and the proton when their spins directions are in the same direction. That is the upper state. When the electron flips, that produces a photon at a wavelength of 21 centimeters. Now, what happens is when that light travels, that radio wave travels to us, because the universe is expanding, the expansion of space-time stretches the wavelength. So by the time it gets to us, it's at tens, even hundreds of meters in wavelength.
Right.
And that corresponds to frequencies below 100 megahertz.
It's the same thing why, like, I know that, like, the cosmic microwave background, when it was released, it was red light. It looked like the surface of a red giant star, say, but it's now been redshifted into the microwave spectrum.
That's right. It's only 2.7 degrees Kelvin, so 2.7 degrees
right.
above absolute zero, but enough still to radiate prodigiously.
Right, and it's interesting that even though that's farther away than these dark ages that you're talking about, we can see it because there was so much light that was released, and then this time when there wasn't. So that's you right. see just vast clouds of cool hydrogen occasionally releasing these single photons of light when this spin flip transition happens. Taken individually, it's hard to see them, but with the amount that's out there, this stuff starts to add up.
That's right. You've got it. So what we're observing from the moon, what we'll be observing in a few years, is this, what's called the global 21 centimeter cosmology signal. and it'll be a spectrum that we're looking at. So we won't be taking a picture. We won't have an image, but we'll have a spectrum. And that spectrum, which will have good spectral resolution, is filled with all sorts of information about the nature of the universe. We'll be testing our standard cosmology models during the Dark Ages, because one of the things that's exciting about the Dark Ages, as I mentioned before, there's no astrophysics. It's just the expanding universe. And so any deviation we have from that simple model of just an expanding universe is going to tell us if there is new physics that we haven't seen before. So physics having to do, for example, with multiple kinds of dark matter, about neutrinos, maybe even an earlier epoch of dark energy that some have speculated can exist. So this is a playground. The Dark Ages is a playground to test basic standard models of physics and of cosmology.
And so when you say
that'll be great.
When you say no astrophysics, you mean no stars, no black holes, no neutron stars, just
all the things we're used to dealing with,
no planets
that at later times make the universe messy. Right? Because stars, then they ionize the gas and they interact with each other, and they, you've got all sorts of things that then contribute to the signals that we're seeing. It's very messy. We got accretion disks, we got stars forming, we got planets forming. I mean, you name it.
Right.
The Dark Ages is simple. Simple. And as I said, it's that playground for cosmology that we've never had access to.
And the astrophysics, the messy stuff that you described, that all comes later. The formation of whatever the first stars look like, the formation of the first galaxies, and to create the modern universe that we see today requires all of these different building blocks coming together bit by bit to give us what we see. And I know there's been plenty of simulations run that attempt to recreate the universe as it looks today, but still that, it's called Dark Ages for a great reason. We do not know what was going on in those earliest points. So you've talked about the Dark Ages. You've talked about this ability to peer into this. What else is interesting that we're able to look at with this kind of with this wavelength, this one that's capable of seeing into the 21 centimeter?
Yeah, another thing that we've been looking at, I mentioned to you before that we can start off with simple radio telescopes. The next one after that will be an array of radio telescopes. In fact, just behind me in this picture, you can't quite see it very well, but the astronauts are trying to lay out a series of radio dipoles antennas and to form an array like the VLA or like the OMA telescope, but except operating at low radio frequencies, where the technology is very simple, just dipole antennas. Okay, like the old TV antennas you see on people's roofs. That same kind of antenna technology laid out over tens of kilometers. With that, we can do another piece of astrophysics that we've not been able to do before, and that's look for magnetic fields associated with potential habitable planets in exoplanetary systems.
Right.
So how does that work? Well, what happens is we look in our own solar system is when our sun bursts and it creates a flare or a coronal mass ejection, it hits the magnetic field of the Earth and lights up the magnetic field. It produces an optical aurora, which we're used to seeing, but also a radio aurora as those charged particles spiral in the magnetic fields. We can use that same idea now applied to planetary systems that are being discovered by the TESS mission within 20 parsecs, 30 parsecs or so nearby star systems. And similarly, when those stars burst, and a lot of these stars are M dwarfs, so they tend to be more active, and they collide with the magnetic fields of those planets that have magnetic fields that will light up and produce a low frequency radio signature. This, in fact, is the only way we can confirm whether or not a potential habitable planet has a magnetic field. Why am I making such a big deal out of magnetic fields? That's why we're here. Without the Earth's magnetic field, life would not have bloomed on this planet. Compare that to Mars. Mars had a magnetic field at one time, and we know from the MAVEN spacecraft mission that over time its field shut down because Mars' core is smaller. It cooled, magnetic field shut down, and then the atmosphere began to be stripped away. Mars once had an ocean, we think. That's all gone. The atmosphere is gone, and it's very much a desert planet. Contrast that to the Earth, which is rich in life. So if we're looking for places that are potentially habitable planets, or maybe life is there, we also need to determine if they have magnetic fields. We can do this with our lunar radio telescope.
I think that's a kind of a mind-bending idea, that not only can you detect exoplanets, literally detect exoplanets as they're being buffeted by the solar wind of their star, but you're also confirming at the same time that they have a magnetosphere, the kind of thing that we know is probably critical to life here on Earth, that we wouldn't have the kind of complex life forms. So it's kind of a twofer. Like you're detecting a planet and also a potentially more habitable planet than one without a magnetosphere. I'm assuming is also, like with the traditional planet hunting techniques that we have, you've got the radial velocity method, you've got the transit method. With this, you don't need to have it lined up in front of the star, right? You could detect it if it was off axis, couldn't you?
Well, that's right. So the angular resolution that we get with the radio telescope array with this interferometer allows us to know that the radio emission is coming from the direction of this given star system. The resolution isn't good enough to be able to actually image in the radio the planet, but the radio emission has a very distinct set of characteristics in terms of polarization of the light, the spectrum of the radio emission, I should say. And so we can tell that it's coming from a planetary magnetosphere. And depending upon the frequency, Fraser, we can actually tell you what the strength of the magnetic field is.
That's amazing.
So that's really cool.
And so that would tell you whether or not it's enough for it to be protective for
exactly.
The
so you can further model this.
Right.
So if you find a rocky planet in the the water zone around an exoplanet, looks interesting. The radio emission can also tell us about how active the star is, because like our own sun, when the sun emits, for example, coronal mass ejection, it also produces a type 2, type 3 radio bursts. So we can study the space weather, see how active it is, and we can measure, in principle, the magnetic field. You put that all together, if it's a rocky planet, it's the right place, it has a magnetic field, it's like, ooh, man, we got it. Okay, let's focus our attention on this planet.
Right.
This is a good one for us to study in more detail. Can we pull out what the atmosphere looks like? Are there any indications of life? Maybe, they've done the same nasty stuff that we've done to our atmosphere, and they've put, extra carbon into the atmosphere. We can methane, and we can, potentially detect those and begin to study. And maybe some point in the distant future is say, okay, this is where we want to go.
Right.
We want to inhabit that planet someday.
Right.
If someone else isn't already there,
that's a big job.
We're going to go, someday off in the future, 100, 200 years in the future.
Now, I know that we as a modern technological civilization are giving off a tremendous amount of radio emission, the kind of radio emission that would get in the way of a really sensitive telescope tuned into these bands. Are there any kinds of leaked signals that we give off as a civilization that might be detectable by a telescope like this?
Yeah, that's an interesting question. We've pondered this only a little bit. Now, we're operating at very different frequencies than the SETI searches are. The SETI searches are often looking at, 21 centimeter in the hydrogen band or the water band. Those are all at higher frequencies. But, it's possible that we could also see leakage of radio emission from these planets. Everything that we have on our desktop right now, all the power supplies, that you have on your computers, they're leaking low frequency radio emission, contributing to this. You add it up over an entire planet, and it's a lot of emission. Our planet looks very hot in the radio as a result. The brightness temperature of the Earth, when you see it from the near side of the moon, is actually 750,000 Kelvin. So to give you an idea of what the equivalent brightness temperature is. So it looks hot in the radio. It's actually non-thermal, but it has that characteristics. So might we look for radio signatures as well of a early technological civilization? I think it's at least worth thinking about, because the weak signals that we're going to be detecting from the magnetospheres, they're still probably larger than what civilization would be. But as we continue to build this out, we're going to get better and better at doing this. Like, for example, we were just funded 2 weeks ago by NASA from the NIAC program, the NASA Innovative Advanced Concepts. Program, and to look at building a 100,000 dipole array on the moon. And that will be first of all, it'll be the ultimate cosmology telescope, the best, most sensitive one ever built by human civilization. But, also looking at these exoplanets, we'll be able to potentially see very, very weak signals. So, it's something we've pondered a bit in terms of, might it give us a different kind of signal about extraterrestrial life?
So let's talk about the mission. So what is the plan, the feasible plan to be able to deploy a giant, as you say, 100,000 plus dipole antenna onto the surface of the moon? A lot of people, they make this pitch like, we should build a telescope on the moon, but it's like, we can't even return humans to the moon within the next couple of years. It's something we haven't done for 50 plus years. It's far and it's difficult to get to. So to then say, I want to build a massive radio telescope on the far side of the moon, that's a project. So what is the plan?
Well, I would disagree with you a little bit when it comes to the moon in terms of accessibility. The big game changer is the moon isn't that far away. And now you have private companies that are going to the moon. You've got companies like the one behind me. This is Dynetics Human Lander. They've been funded by NASA to build commercial human landers. So they will take not only NASA astronauts, but privately funded astronauts later this decade. So the moon, because of our technological leaps over the last 50 years, is really accessible. But the plan is, we've got a roadmap to do this in stages. So we just don't go to this big array. So the first thing is, later this year, our first US radio telescope is going to land on the near side of the moon in November with one of NASA's new commercial lunar payload services lander, CLIPS, as it's called. And there's a company called Intuitive Machines out of Houston that's bringing it. This is a commercial company. So NASA is buying services. They're going to land us on the moon. It's a simple dipole radio telescope, but we begin collecting data on the environment, the plasma, the local ionosphere, and also begin calibrating our instrument. That's followed a couple years later in 2024 by another mission, already also approved by NASA, to go to the far side into the Schrodinger impact basin. And that radio telescope, coupled with a second one that we're proposing to NASA, will allow us to begin doing cosmology. So that global signal we talked about a few minutes ago, simple telescope, simple technology, we can do with that mission on the moon. Everything's really in place to be able to do that. So that's 2024.
Wow.
Then a few years later, we have, because of NASA funding, we've done a design study with JPL of a first array, which we call FARSIDE. It's actually an acronym, a tortured acronym, but
it's a backronym.
FARSIDE, and it allows us to put out 256 of these dipoles with a single lander, like the one behind me. I'll get this right, like this one behind me here. And a single lander can carry 4 small rovers, which we then deploy using a tether, 4 tethers in a spiral-like pattern. Set this up, and just a single lander with all current technology, no magic, no technology beyond what we currently can do today, and begin operating, and it will have enough sensitivity to detect those exoplanets that we talked about.
Right. So I just want to stop for a second then and just talk a bit about this mission. So you go to the far side of the moon, you land with a lander, it deploys 4 rovers.
Right.
And each rover essentially, and if I recall the proposal, it lays out like a big petal, like a big flower petal shape onto the surface of the moon. And essentially it's reeling out a cable, and the cables have these dipoles embedded inside of them as it's going along, and then it returns back to the original site, and now you've got the rover, the lander in the middle, and 4 petals around it. And so, I mean, it's kind of rough. Like, you're driving along over rocks, you're going over inside craters. Like, it's going to be rough terrain. Is the tolerances of a radio telescope at this wavelength, is it okay with that kind of rough and ready deployment?
Yes, that's the nice thing about these wavelengths. They're very tolerant. So unlike, say, a millimeter wave telescope like ALMA, you have to very, very precisely position the individual dish antennas and know them very accurately. For a low frequency, we only have to place them within a fraction of a wavelength. In this case, that's a meter or a few meters tolerance, so we can easily go around small rocks or small impact craters. So very, very tolerant to the placement where we want to put it down. And the other nice thing about an array is we can even lose one of the arms, maybe one of the rovers. It decides it just doesn't like it. It just rolls over and dies. It's still, with 3 arms, we can still have a very nice interferometer to do a lot of the work that we need. So the nice thing about this study is we've demonstrated that we have the technology. We will have the lander in just a couple of years. They'll be capable of bringing 1.5 or 2 metric tons to the surface of the moon. Multiple rovers. These rovers already have been designed and they're at a high technology readiness level from JPL. We're ready to go. We can do this.
So let's talk about pointing. How do you point a flower petal dropped onto the moon? How do you direct it at targets?
Yeah, no moving parts. No moving. Unlike the VLA that has, we've all seen these pictures of the VLA and all the dishes moving together. This is all done electronically. We steer the antenna electronically. So what we're actually doing, Fraser, is we take an image of the entire sky, or that hemisphere we can see from the far side of the moon. We take an all sky image. It has that field of view once per minute in 1,400 channels of frequency resolution. And all of that data then gets stored back so that later we can go back and look for bursts, for example, from these stars or planets that we were talking about. So we know where the test planets are. So we go back and electronically we can then image just those parts of the sky that we're interested in and do it once per minute to see if there has been a burst in radio emission. So it's all done electronically. Once again, this is what makes it practical to be able to do. Once we deploy it, no moving parts, the rovers are done. We just collect the data and send it back via a communication satellite to the Earth.
Right, and that was going to be my next question. Is the problem, of course, is you're hiding from the Earth's radio emissions, but then you also can't then send radio emissions to the Earth. So how do you get that data back home?
Right. So with the Schrodinger missions coming up in 2024, NASA has already committed to a communications satellite. The Chinese already have such a satellite at the Earth-Moon L2 Lagrange point. That's that stable point in the Earth-Moon system. Sits above about 70,000 kilometers above the far side. So we may build it, that is NASA may build it, we may build it with ESA, but they've committed to have that in place for that time. It's I mean, we won't go to the far side without that communication satellite.
Right. And I mean, a satellite like that would be useful for communicating with the South Polar region. There's all kinds of value to having one there.
Yes.
And in fact, the Chinese satellite, I forget the name of it, has a Dutch radio telescope experiment tuned to that wavelength. So it's almost like a pathfinder for what you're trying to do. Have you been watching and seeing what they've been able to accomplish with that satellite?
Well, more so, I've been talking regularly to my Dutch colleagues who are collaborators on this array project. So we talk pretty regularly. The Netherlands China low frequency Explorer it's called, does operate in similar wavelength regime. They've got two problems though. Number one, at the L2 Lagrange point, the reason that's attractive for communication satellite is because you can see the far side and the Earth at the same time. Well, we really don't want to see the Earth, right? I mean, the Earth has got lots of radio frequency interference, so it gets blasted with that. Plus, the other problem is they designed this pretty quickly, and they didn't really isolate onboard radio frequency interference. So unfortunately, they're seeing a lot of interference from all of the other electronics we were just talking about, all the power supplies, the computers, everything blasts out at these radio frequencies. So it still is a pathfinder, still is a great idea. Unfortunately, their antennas did not deploy fully either. So they had some technical problems, but they're working away on the data analysis. And, you know, I think they'll get some useful precursor information. So we're talking very regularly about what results they might be able to produce.
And that's what I had heard, that despite the fact, as you say, the antenna didn't deploy correctly, despite the fact that the Earth is this blazing spot of radio emissions, despite the fact that the spacecraft itself isn't properly well shielded from the emissions it's giving off, it is still giving some kind of tantalizing looks into the dark ages, which is exciting.
Well, I don't know about the dark ages. I don't think it's going to be able to peer into the dark ages, but
the reionization,
it is observing at these frequencies, so it'll be able to maybe see some of the radio emission from the Earth, possibly solar bursts, these type 2 and type 3 solar bursts, but it'll help us define what the problems are in observing in space, and to solve those for the future.
Yeah. I mean, people always ask me, like, is there any reason to put a telescope on the moon? And my answer has mostly been no, that it's just so difficult to try and put a telescope on the moon, and the benefits that you get, better to have a space telescope or whatever. But in this case, because it can be rough, because you are in the lunar shadow, it's the perfect kind of telescope to do that. It would be relatively inexpensive. What kind of budget do you think? Like,
I've been telling people that for years, for 35 years,
yeah.
To do this, but still getting to the moon was tough. That was the tough part. And that's where I would get raised eyebrows, that it's still too far off. Now, I mean, we're going to be at the moon, every few months.
Yeah, the Chinese just brought a sample back.
Yeah, exactly. So for example, my Dapper telescope that we have proposed for the far side with the Lucy instrument on the Schrodinger is $10 million.
Yeah. Nothing.
$10 million to open up a whole new part of the universe.
Yeah,
that's a pretty good price.
Yeah, and so now that there are commercial landers, that there is
to do that. So I hope the NASA reviewers who are going to be looking at this over the next month or two are going to look at that and say similarly, wow, what a bargain for the science we're going we're going to be able to do. And again, since they're already going to the moon, they're already committed to that FARSIDE lander, carry this along as part of the mission, and look at all the wonderful astrophysics and cosmology that you get to do that. Because NASA is paying about $100 million for the lander itself, and it's going to be carrying a number of other payloads too. They're going to be really great for lunar geology, understanding the lunar environment, so carrying us along to do the first cosmology, it's a good investment.
So now you mentioned,
I'm biased. I think it's a good investment.
well, I know it has a very special place in my heart. I literally won't shut up about it. So I think if whatever I can do to help give you the bump, the Universe Today bump to what you're doing.
There you go.
But so now you talked about this is the small version. So what you mentioned, a version that could potentially have more than 100,000 of these dipole. What does the scaled up version of this look like?
Yeah. So the scaled up version, what it will do is it'll be laid out over about 20 kilometers, and it will have sufficient resolution. So in cosmology, what we'll be able to do is see those fluctuations of the dark ages that are produced by density variations in the early universe that will later become those first stars and galaxies. So that adds another dimension. Just like the cosmic microwave background. So first we did the black body spectrum. That's what COBE did. Then that was followed up with WMAP and Planck. And there they were looking, you've seen the pictures, the pretty pictures of those temperature fluctuations. They correspond to density fluctuations. We'll do the same thing with this array.
Wow.
Only here it opens up then all of that kind of advanced physics that we were just talking about. We can independently estimate neutrino masses. We can look for another epoch of dark energy. We can look for warm dark matter, cold dark matter, fuzzy dark matter, sterile neutrinos.
Right.
Imprints of inflation at high perception. All of the modes of overdensities that we can't see with the CMB and later. So. Tremendous. I mean, this is really a physics machine as much as a cosmology machine to be able to do that.
I mean, I know
but the signals are very weak. That's why
Right.
we need 100,000.
Right.
The more it's like any telescope, right? It's like a big light bucket, and the more of these you get, the more of a radio photons we capture.
So what does deploying a one of that scale? I mean, we talked about the small version. You've got this single lander with its multiple rovers that are deploying the lines around it. What would it look like when it's in that largest operation, and how would you sort of physically do it?
Well, that's one of the things we're studying. One of the big differences, and the reason that we're working with the Lunar Resources Company in Houston, is they have a technology to actually be able to manufacture the antennas from the lunar regolith, from the lunar soil. The lunar soil has a lot of aluminum, for example, so you can use an electrolysis approach to actually plate these antennas onto the surface of the moon. So rather than hauling them all from the Earth, which, as you know, launch costs are extremely expensive. What you do is you manufacture all the wires, the solar panels. You can do the same thing, manufacture them from the regolith, the antennas, and then lay these things out. So the idea is once we get FARSIDE going and we set up shop, we get power station, we understand the process, then we continue to expand this over a period of 2 or 3 years, which we think we can do very efficiently. Obviously, we'd have more of these rovers. We probably have 8 or 10 or more of these rovers operating, teleoperated from either the Earth or from the moon. People, astronauts doing this teleoperation. A lot of automation associated with that as well. So that's how we make that leap from 200 of these, where we bring everything from the Earth, to then 100,000, where we manufacture these things in place. And of course, NASA's excited. One of the reasons I think they funded us is NASA's excited to use this kind of technology for other things. This is how we begin to live off the land, as we will eventually need to do on Mars as well.
Yeah, I talked to Alex Ignatieff from Lunar Resources a couple of months back about this idea and just this possibility that you could have a rover just going along on the surface of the moon, gobbling up regolith,
right,
and laying down a track of solar panels and dipole antennas as it goes. Again, it just seems perfect that you've got this. That because the tolerances don't have to be as high as if you're building an optical telescope or an infrared telescope or whatever, that you can have impurities in your material, and as long as it works, then it's going to be able to participate in the science. How big would this telescope, would the field be that you've filled with?
Yeah, so we put 100,000 of these down into an area that's 20 kilometers by 20 kilometers, roughly. Right. So there'll be more tightly packed in the center and less so as you go further out, which is pretty typical for these arrays of radio telescopes.
That's amazing. I love the again. I do really like the idea. It feels
well. One of the things that Fraser, that's exciting about this epoch of exploration that's different from Apollo. I like to talk about, in this case, unlike Apollo, we're going to take Silicon Valley with us to the moon. So all of the technologies that didn't exist in the 60s, so robotic technologies, being able to, this electrolysis approach, in situ manufacturing, AI to be able to operate the rovers and the deployments, all of those advances are coming with us to the moon. That is going to make exploration, is going to make construction, is going to make doing, radio science just possible now in a way that we couldn't even think about 50 years ago.
Yeah, it definitely feels like, as you say, 50 years ago, it took the economy of, one of the largest economies in the world, and they spent probably 10 times the budget of NASA today. I think the price to do the Apollo
it was about that. Yeah, it was about 5% of the budget. Today, NASA's budget is 0.4%,
right?
Of the U.S. budget. So yeah, it was 10 times more equivalent in those days.
Yeah, it was $350 billion in inflation-adjusted money to run the Apollo missions. And so, but the technologies have been getting better and better. You see what's happening with SpaceX, with reusable rocketry, with the miniaturization of technology, with the launch of CubeSats, with all of this stuff that's coming. So it's like the cost, the price to do these kinds of things. I mean, again, I can look back through old NASA research documents and dig up dozens of let's build a telescope on the moon ideas.
Yeah, that's right.
But it was always too expensive. It was always crazy.
It was too expensive, it's too advanced, too difficult. But now the technology is caught up. I mean, you get these small companies, that these are startup companies, Intuitive Machines, Astrobotics, Maston, Space. I mean, they're startup companies that are building landers to go to the moon, and they have a business plan that they think they can make do by carrying NASA payloads, ESA payloads, private companies to do experiments on the moon and make that work. I mean, that's astounding to think about that, in contrast to what you said, that it took the resources, the entire resources of the most wealthy country in the world to just get to the moon in 1969.
Yeah. And so, people always ask me, like, when are we going to have human civilization? When are people going to live on the moon? When are people going to live on Mars? And it's always sort of, in my opinion, it's going to take a lot longer than we think for people to actually have cities. But eventually, if as the technology continues to ramp up, we will trivialize this process. And it's sort of that same thing, like what will it take for you to hop on an airplane and fly across planet Earth for a couple of days?
Exactly. I mean, you look at Jeff Bezos, the Blue Origin company. Their philosophy is one of the things when I've gone up to visit them, they talk about having a 100-year plan. What company talks about a 100-year business plan? You know, I mean, of course, when you're funded by a billionaire, puts in $1 billion a year into the company, that makes some difference. But they've got this outlook, and they've got, you know, over the next few decades, they are talking about hundreds to thousands of people living on the moon. And that's something they want to do privately as well as with government investment. So things feel very different now than even just a few years ago when you're talking about the practicality of space exploration, building advanced telescopes, habitats, science stations on the moon like what we have in Antarctica. So all of that it's going to be possible this decade.
What other, you know, setting aside your project specifically, what are some other uses, practical uses, do you think of the moon, the far side of the moon, for specifically science, I think?
Yeah, well, the far side is particularly exciting because it has the oldest impact basin in the entire inner solar system, the South Pole Aitken Basin. And it was a huge collision with the moon about 4.3 billion years ago, if I remember correctly. And it hollowed out a big piece of the moon, a lot of which is just lying there right on the surface to be picked up. So as you know, that, you know, our planet, the moon, evolved dramatically over time. Impacts from a lot of asteroids, but also from, in the case of the Earth, the oceans, the plate tectonics, the atmosphere, and a lot of that history is gone. On the moon, it's there. It's there for the taking. So one of the things I like to tell people about, why are we going to the moon scientifically? Well, it's about our origins. I talked about, you know, it with cosmology, being able to detect those first stars. Because ultimately, in order to get to the Earth, our sun, which is the third generation star, we had to start off with that first generation. I want to know what that first generation looked like, okay? So that's one part of it. The other origin story is the origin of the Earth-Moon system. And that history is on the moon. It's our history book, including this late heavy bombardment time period when life was just beginning on the Earth. So that's recorded on the moon. It's gone from the Earth. So what can we learn about what the role was of all of that bombardment several 100 million years after the Earth-Moon system formed? What role did it play in creating life on this planet? So even fundamental things like that.
I think it's even
very exciting science.
Yeah, I mean, it's even deeper than that. The surface of the moon, the regolith itself, acts a bit like a tree ring, like a core sample of not just the history of the solar system, but almost the history of the universe for 4.5 billion years, for as long as the moon has been around, as long as the regolith is readable. And so you could actually detect gamma ray bursts that went off nearby, neutron star collisions. They would be written into the regolith like layers of mud at the bottom of a
that's right. And the other thing about the moon too is, getting back to basic physics, it's a great detector for cosmic rays and neutrinos. You know about IceCube, which is in the South Pole, used to detect neutrinos. The reason it's used is because it's just making use of the ocean and the ice there for a big detector. The moon is a much bigger detector. So if you want to see neutrinos from distant active galactic nuclei, distant supernovae, then the moon is the place to go. Similarly, having a giant cosmic ray detector, some of which you can do in the radio as well as in the visible part of the spectrum. So, you know, the moon is just, it's a big, dumb body, but it's a wonderful detector. It's a wonderful place to do our astronomy from, as well as learn about solar system history.
And it is interesting, just this idea. You can do these two things at the same time. You can deploy on the moon, build your telescope, start to do the science, start to study the moon, and at the same time, you're learning how to live in a closed environment off the planet Earth,
right,
in a place that's trying to kill you every way that it can imagine.
It is,
Yeah.
and you're only 3 days away though, in case something goes
Right.
wrong.
So if you run out of toilet paper, they can send you more.
You can make it back. Whereas you go to Mars, and I mean, you're committed for 2.5 years. So we better figure out how to live on the moon first, to mine water from the South Pole, because we're going to need to and turn it into rocket fuel or whatever we want to use it for, because we're going to need to have all of that capability when we're at Mars.
Now, I just want to sort of go back to the NIAC grant that you were awarded. So what was the amount that you were awarded from NIAC, and what is the deliverable that you now have to send them?
Yeah, so the initial award is modest. It's one of these phase 1 grants, so it's $125,000, and it's only a 9-month study. But what it does is we really set up defining the problems. So we lay out what NASA likes to call a science traceability matrix. So how do we start off with the big science questions, and then that leads to what's the instrument requirements, the power, the frequencies, and so forth that we want to operate in. So what is that science case? How will we try to implement it? And then begin thinking about some of the design requirements, some of which we were just talking about. That is, how do we scale up from a couple hundred dipoles to 100,000 dipoles? What does our in situ manufacturing technique, what is that going to require on the moon? What sort of factory, if you will, are we going to need to be able to do that? The data handling. We've never had a radio telescope with 100,000 components. Even the SKA, has something like 1,000 antennas or so, and others, have less than 100 at the current time. So the amount of data and the data correlations we're going to make is enormous. So we have to think about, how do we handle that? How do we do processing on the moon? What does the power look like? Are we going to use solar power, or are we going to use nuclear? Because we're at the stage now where NASA, working with the Department of Energy, has developed these small nuclear power reactors. These are fission reactors that you can take to the moon and develop, hundreds of kilowatts of power. So would we be looking at that? So some of the practical things. So mainly in this first phase is laying out the problems, the overall design, and then we will apply for a phase 2, which would then allow us to begin actually trying to implement some of these and doing experiments in the lab and doing experiments on the ground, and advocating for getting a prototype on the moon to actually work this through in a real environment.
But it's sort of a different pathway than, for example, other more established, missions, more plans. Like it's a different pathway in walking down this technology road. I mean, at your university, you're involved in many space missions that are out there right now. So why this path, going through the NIAC method, as opposed to necessarily creating a proposal to respond to, say, one of the decadal survey challenges?
Yeah, and we're looking and hoping for. We submitted the FARSIDE array to the decadal survey, and we're looking for a recommendation. And therefore, NASA treats the decadal surveys very, very seriously. And so, with a shout out from the Astrophysics Decadal Survey, this would provide momentum and potentially funding to begin working towards a phase A study of the FARSIDE array. But what NIAC does for us, it allows us to also think beyond the FARSIDE array. So getting started about thinking about what is this going to look like, this array in the 2030s, which is probably what we're talking about here. So that's why it fleshes out this roadmap that I mentioned before. So we have really near-term stuff beginning later this year, all the way to 100,000 dipole array in the 2030s, and things in between.
I got a great question from the audience. From Arjona is asking, what would a prototype look like? Is there anything that could be built in a desert on Earth? Could you build a telescope autonomously here on the planet?
Yeah, and early ones of these have actually been built. We're building a small telescope called the Cosmic Twilight Polarimeter to test out our Dapper antennas and our technology. And this is going to be placed in Green Bank, West Virginia, at the National Radio Astronomy Observatory. My colleague Judd Bowman at Arizona State has placed the EDGES telescope in Western Australia, again, a single antenna to begin doing that. And then in addition, in my lab, working with undergraduate engineering students, I have a telerobotics lab. So what we've done is we've put together working models of rovers with robotic arms that we then teleoperate to place antennas to do some problem solving. And recently we've imported all of this inside the computer. So we have a virtual and an augmented reality versions of the identical rover and robotic arm, in which we can do rapid prototyping and problem solving and eventually training for astronauts who would do this. So all of that is happening today. All that's funded by a combination of NASA and also some industry funding from Lockheed Martin.
Terrific. Well, we've reached the end of our time, but I've been keeping a very close eye on what you and your team are working on. We report on it regularly on Universe Today. I've done videos on it, and often we talk about this in the show. So I know also in the chat, a lot of people are big fans and quite excited whenever people ask me, why don't we just build a telescope on the moon? The Farside is the
we're going to do it.
Yeah,
we're going to do it.
Farside is the one that I bring as the example of what I think is the first practical step, which fills in a piece of the universe's history, which we have almost the least amount of information about. So it's a sort of valuable instrument and a sort of worthwhile project to do. If people want to track what you're working on, learn more about it, where should they go? Yeah,
we have some websites that for the various projects you can just Google on. You can Google on my website, our website for NESS, N-E-S-S. There's one for Dapper and one for Farside. So you Google on those, radio telescope with those names, all of those websites will come up. They're cross-linked to one another. We've got published papers, we've got videos, we've got talks and so forth, all embedded in there. So, join the movement. It's a movement. We're moving towards the moon.
Moving to the moon. All right. Well, Jack, thank you so much for taking the time to chat with us today. Really appreciate it, and good luck with the project. And keep us posted when you.
Thanks very much. Really enjoyed it today.
All right. Thanks a lot.
See ya.
Thanks, everybody. We've got. Well, that's not the right one. Okay. We've got another interview coming up tomorrow at an hour later. So there's a bunch of interviews from various NAC grants coming very quickly. So stay tuned. All right. Thank you, everybody. And now end stream.